Hi everyone. In this video, we're going to look at digital fabrication techniques following the polyhedron models that we have been developing. For this exercise, I chose one of the earlier example files where we looked at these volumetric elements on truncated icosahedron. So let's actually get to know what this file was doing. So we have a polyhedra. Let's actually look at the polyhedra. This is its geometry, and we can see that we are dealing with pentagons, five-sided polygons, and truncated hexagons. So these are the six-sided polygons. And this polyhedra actually gets a nice distribution. So you get these pentagons actually surrounded with truncated hexagons. And I use that aggregation as a principle to look for the number of sides to do some dispatch filtering. And we get basically a separation here. So we separate pentagons and hexagons. And I took the pentagons and extruded them outward using these operations here. So we are basically getting the centroids, defining a vector. Let's actually first look at this one. And let's hide the polyhedra as well so that we can see the geometry clearly. So these are the cells, and then we get these vectors defined from the centroid of the polyhedra. Then we move the cells outward. We scale each cell in its place. Then we also have basically an inward scaling as well. So this is the piece that moves inward. So we have a scaled outward projection and a scaled inward projection. And then I combined these three into lists and lofted them into these cones. So the top of the code is actually doing something similar. So let's quickly look at that as well. It's actually doing it at a lower threshold. So you basically get, let's actually bake some of these so that we can see a bit better. So this is one of the sides of this geometry. So you can see that we have a scaled inward version and this piece right here. And so you can actually define these elements any way you want. You will basically get surfaces that we can build using various material like paper, because I was thinking that these could be actually folded pieces, so that we can actually unroll them and fabricate them as well. So that's what this tutorial is going to be about. So how can we actually work with this model and prepare it for digital fabrication? So I'm going to work on this bottom portion because this will be easier to visualize and see since these elements are separated. Now I want to show you what actually happens when we try to unroll these elements. So let's bake one of these, and so this is the geometry that we are dealing with. I'm not working with any sense of scale at the moment, but let's assume that we're working in centimeters. I actually have meters as units, but that's not going to be a problem. So let's say this, we are fabricating this out of paper. Now we have to basically cut some material in these geometries. So if we want to achieve this shape, then the material has to be fabricated in a way that these pieces will be connected. One way of doing that would be to actually explode this and fabricate each piece. So I'll just show you what I mean by that. So if there's a command called unroll surface. So when I do unroll, I can actually explode the elements. And when I do that, it basically outputs all these little pieces of this individual geometry, but you can see that it's really hard to guess where these pieces are located in the whole piece. So one way of finding them is to label each piece. but once you label, you actually get a lot of tags placed on the object and on individual pieces. So this becomes almost like a really complex puzzle to produce something simple like this. So I was thinking whether we could actually do it in another way. So if you look at unroll again, let's turn off labels for now, and let's not explode this geometry. So when I unroll it, this is actually how it outputs the geometry. Now, one thing that is nice about this is that you can see that the top pyramid, let's call that a 5-sided pyramid, and the bottom pyramid, they're connected and they're separated as well. So we actually get these individual elements joined. So if I fabricate or cut this out of some material, basically these will be folding lines, and the outward boundary will be where we cut, basically. But some issue here is that once you have a lot of these pieces and you want to lay them out on a piece of material, you can see that these elements are going to be kind of an issue for packing these in not sort of a wasteful way on some material. So I wanted to change this in a way that doesn't create any sort of waste. So one way of doing that is to actually break this inner element in a way that it won't create a problem for us when we unroll it, so that all the pieces will be connected, and these will be kind of the joining elements for these pieces. So I'm actually going to show you how we can achieve that in the script. Basically, we are working with we can actually work with one of these first. So let's actually do list item here and just get one of these elements and just work on that. Now what I want to do is, as I said, disconnect this bottom half in a way that it creates flanges for each of these corners, and when we unroll them, we get a continuous piece, but the flanges would be joined to each individual top face. One way of doing it is to look at, we have to find this bottom edge here, which is located here. So I'm going to bring this down. And we also need to work with the original shape, which is right here. So I'm going to explode the original polygon, and I want to also explode the scaled lower half. And when we explode the curves, we actually get these segments and vertices created. And I want to operate on these lower segments, and I want to scale them down a bit so that their sizes shrink and these corners are broken. So we can actually do a scale here. So I want to scale each individual segment. The center of scaling will be their midpoint. So we can do point on curve. So the point on curve will use its centroid, and the factor could be, let's call it 0.8. We need this to be a number that is lower than 1. So these are the resulting geometries. If you can see them, they actually do not overlap with the existing geometry. They're actually smaller in size. I'm actually going to turn off this loft and this geometry so that we can see this a bit better. There you go. Let's actually bake it and fit to it so that we can actually zoom in and out a lot better to see the geometries themselves. So these are the scaled versions of the vertices, and the next operation is to actually connect them to these top elements. So we have 5 curves here, and we have 5 curves on top, and we can just do a weave function here. You can also do merge, but what weaving does is it actually combines these elements. So if I were to let's look at grafting, it will actually connect them in lists of 2. So these would be grouped, and now if I do a loft, these will be the flanges. One advantage of modeling it this way is that the top portion now would actually connect to these elements, but since these are not connected, when we unroll them, they would open up, so we will get a better piece for digital fabrication. So I have these elements now. What I want to do is look at the top portion, which we have here in the loft, and take off this lower half here. So I'm going to take this off from the merge. Now this is the top portion, and this is the bottom portion. Now we have to join these two elements together in a way that that will work for us. But before I do that, I actually want to replace this list item here so that we check that this operation is working for all these members. And you can see that all the flanges have been created in the same place. Let's actually go ahead and turn off these parameters here as well. And what I want to do next is to join the top loft and the bottom flanges. Now, when you look here, we actually do have a problem. So we get lists within lists. So if I were to right click and simplify this graph, you can see that each list actually contains 5 flanges. So we get a double streaming data here, and we need to make it match the top loft here. So I'm going to simplify this loft too. So you can see that we have each loft placed in a list. We have 12 total, and we need this to merge with another list that contains all the bottom flanges as a list of 5 elements. So one way to achieve it is to use partition list. Partition list basically takes a group of items and breaks them up into sublists using a size. So remember that we are working with 5-sided elements here. So we have pentagons. So if I were to divide up this list into chunks of 5, so let's get the list. But we have to put this into a single list. So I have to right click here and do flatten. We don't need simplify anymore because flatten would actually render it as a simple list. And now 60 items go, all the flanges go in a single operation, and they come out as lists of 5. Now this would basically require us to merge with the top list, but you can see that the chunk also creates this secondary operation. We can simplify it as so, and we get 12 lists containing 5 flanges. Now we can merge these 2 data streams, so the bottom list and the top list, and we will get each piece now organized in a group of 6. And the last operation would be to join them. So if I do brep join, the brep join basically gives me basically joins all these elements in the sublists. So all the 6 items in individual lists, they will be joined. Now we get the final shapes. Let's actually look at them. So I'm going to bake these, and there you have it. So this is kind of the modified version of the bottom flange. And why did we do this? Why did we have to break these corners? It's because now if we were to do the unroll operation, let's actually look at that. If I were to unroll this piece and turn off explode, we get a piece that looks pretty nice actually. So you can see that this element now, we can actually fabricate this. So if we cut this out of some paper or some material, we can fold all these corners, and we will acquire this shape in a continuous manner. We also need to add one more flange here, which is missing. So there needs to be one more element here. I'm not going to parametrically model that, but once you unroll these, you can actually add one more flange here so that this edge joins to this edge. You can maybe use it some adhesive material to actually make this into a cone shape. Okay, now that we have solved this issue, I want to basically discuss some aspects of digital fabrication. So first things first, what I want to do is, well, these elements are pretty much consistent, right? We have the same element 12 times actually. So you might be wondering, why do we need to unroll each of these individually? So you might actually do produce one element and just multiply it. For instance, if I were to just bake one of these, so let's say that we are baking this one and we unroll that. Now there's my surface. Now we can make 12 copies of this on a sheet and we can actually, let's say that we arrange them in a way that fits into the material that we're going to cut them out of. But let's this will only work if the pieces are identical. In cases where the pieces are not identical, this won't work. So let's actually make these non-identical. And one way to do that would be to modify the top extrusions. So I want to change how much this vector actually moves each of these elements. So you can see here that we are getting a distance from the centroid, and this kind of looks identical. What I want to do is basically override this vector here and multiply it with some coefficient. So we can do a random function here, and we can define construct domain. We can define a custom random domain. Let's call it the lower threshold to be 0.3, so that we get some extrusion no matter what, and the upper domain to be 1. And we need 12 of these, but we can get that number from the list that we are operating on. So we want list length, and if I get the list length here, we get 12 elements. So we get basically 12 values, and I want to override the magnitude of each vector here. So we can simply multiply the length of these vectors. You can see that this data is grafted. We need this to be grafted as well. So let's graph this part. Now you can see we have actually modified the length of each of these vectors. The last operation would be to do vector amplitude, where we change the length of these vectors. So I get the vectors, and this will be their resulting amplitude. So what I'm doing here is basically all of these vectors have the same length, but I'm scaling them up with a coefficient between 0.3 and 1, so that their lengths will be different. And I'm going to put this as the under the translation. Now the displacement is there, and but the problem is probably at the merge. So if you look here, because we added this operation here, that's actually causing the merge to not work. So because we get one more data stream added. So you can right click here and do simplify to both data streams, and that will make them merged in a single list. And you can now see that we get different lengths for these elements. Now if I were to bake each of these, we need to know where these elements are, right? Because they're all unique. So if I were to unroll these, each of them would actually give me a different geometry when they're unrolled. So you can see that we actually need to know where this piece is in the whole assembly of the polyhedron. So that's actually what we're going to look at in the second part. We are actually going to take these elements and automate the digital fabrication process, and also add tags to basically know where the pieces are in the flat version on the sheet, as well as in the 3D assembly, so that we can actually put them together as almost like a puzzle piece.